Hello, physical science. I wanted to show you how to do some ionic bonding with polyatomic ions. Just to show you how it works, to take the intimidation out of this word here. Okay? So we've talked about ionic bonding before and what it's about, in that it's usually between one positive ion or one cation and one negative ion or an anion. And it's when they bond together because opposites attract, causing the ions to stick together in a bond. Okay? So we talked about last time some basic ones like sodium chloride, where we had sodium, which has one valence electron, and chlorine that has 7. And we talked about how not just chlorine, but both sodium and chlorine want to have valence shells that are full. And remember, sodium has a energy level below this, and so if it got rid of the one there, it wouldn't, it would still be happy. So we talked about how basic ionic bonding is where a element that has very few valence electrons will want to give those away to a element that has a lot of valence electrons, because this one doesn't want to have so many and this one wants to just fill up what it needs. So remember that ionic bonding is usually between a metal and a non-metal. Okay? In other words, one thing from the left side of the table over here bonds together with something on the right side of the table over here. Metals, alkali earth, transition, post-transition. Those are all metals. And then our non-metals and our metalloids will bond together. Okay? So that's just a summary of the basics, what we learned last time. With polyatomic ions, it works just the same. It's just that one of these two things is not going to be a single element. It'll be multiple elements at once. Now, I've included on this assignment, I've included a list of polyatomic ions. If you got one of these in class, I had it on the back. Oh, mine's upside down. It looks kind of like this. Mine's color-coded. Yours isn't. I color-coded mine by charge or oxidation number. Okay? But in any case, that's, this is something you'll be using today along with your periodic table. So make sure you have both of those handy. So with polyatomic ions, if we look at some of them, let's look at one like ammonium right up here. It's one of our first ones. It has a name, which is ammonium. It has a chemical symbol, which is NH4+. This is the stuff that makes up ammonium, so 1 nitrogen and 4 hydrogen. And when they bond together, they have a charge of +1, which is shown here under oxidation number. I have on the bottom here, remember, oxidation number just means your charge. Okay? So that's ammonium. That's a +1 ion, polyatomic ion. See, it's an ion which has a charge. It's a cation. It's just made out of more than one atom. Okay? Same thing with something like carbonate. Carbonate down here, here's its chemical symbol. It's made out of 1 carbon and 3 oxygen. And notice when it bonds together, it says it has a 2- or a -2 charge. Okay? That's all these are. All the polyatomics are ions that are made out of multiple different like multiple atoms of certain stuff, and they have a charge after that happens. Okay? So let's try making a bond between, let's say, our first ion, ammonium, so NH4, and another and another element here. So we already have a cation here, so in order for this to work, we need a negative ion to go with it. So if we look on the periodic table, let's take chlorine, for example, our classic chlorine. We take chlorine, and when it wants it, so this means when it has a plus charge, this means that it wants to become a plus ion. Chlorine wants to have a negative charge, and they're both, so one is +1, one is -1. When these charges on top here, when you add them together, you get 0. This means that these two will want to bond together. If you want to look at it, NH4 is similar to sodium in that it wants to get rid of one lone electron to become happy. So when it tries to bond with chlorine, which has that 7 valence electrons, it'll give up 1 to chlorine to become a +1, and chlorine will become a -1. And so our overall equation will be NH4Cl. Okay? Not bad so far, right? Because you only needed one of each to bind to each other. Let's take a look at what happens if we have a polyatomic and we need multiple of it. So for example, let's take a polyatomic that's a -1 this time. I'm going to go and I'm going to choose this one down here called hydroxide. So I have hydroxide, which is OH, and it has a -1 charge. Right? According to that, it has a -1 charge on here. And let's put it together with something that has a +2 charge. On here, let's use calcium. Calcium, when it becomes an ion, has a +2 charge. So this means that calcium has 2 electrons that it gives away, and hydroxide wants to take 1. However, this doesn't help because you'll notice our ion math, or like our charge math, +2 plus a -1 equals +1. We're not at 0 yet. We need to get to 0 to be happy between all of these. So in order to get rid of our +1, we need to add -1. So we need to have +2 plus a -1 plus a -1. And we can only deal with these 2 ions. So that means that we have to have 1 calcium and 2 OHs. Okay, in order to get 0 for a charge. Okay, this means we have one calcium that has 2 extra valence electrons it wants to get rid of. OH essentially is like chlorine and has 7, basically. One OH will take 1, and a second OH will take the other one. Now this Lewis dot structure, this dot diagram is simplified because I'm equating OH to something that will gain 1 electron to have a -1 charge. This is essentially how it works. And so when you write your formula down, Ca, and we leave it blank because there's only one of it. Then we have OH. But newsflash, if I put a 2 here, what does this mean? Does this mean that there's 2 OHs, or does it mean that there's 2 H's alone only? It means that there's 2 H's, right? This 2 here does not travel over to the O. So this is not how you would write this out. Since OH is a entity all on its own, what you have to do is you have to take your OH and separate it in your formula with a set of parentheses around it to dictate or let people who are looking at this formula know, hey, hydroxide or OH is all by itself. Then if I add a 2 here, now this 2 is for everything in these parentheses. Okay? Now wait a minute. What if I had something where there was multiple of these and a polyatomic? Let's look at that. Would we do the same thing? So let's take a polyatomic that is at least -2. I think I'm going to take phosphate down here, which is PO4, and it has a -3 charge. And then for our positive one, since we need a positive to go with our negative, let's choose lithium. Lithium wants to become a -1 since it has 1 valence electron. It wants to have a +1 charge. Find out how many lithium you need by doing your charge math. So it's essentially +1 plus a -3. Okay. This ends up to be -2. So we need to add more pluses to get rid of our negative. We need to essentially have +1 plus 1 plus 1 plus -3 to get to 0. This means that we need 3 lithium to go with our phosphate charge to get 0. Right? So essentially it is 3 lithiums with 1 valence electron apiece. And you have phosphate which is essentially like another -3 ion, like nitrogen, because remember they have a -3 charge. So phosphate essentially has, let's see, I'm going to do that to make it easier, is essentially like this generally, and lithium, each of them is giving phosphate an electron. Okay, that's essentially what's happening here. This is how I figure out like how many lithium I need with charge math. This is how you figure it out with a Lewis dot structure. Okay. And then when you write this, you have a 3 next to your lithium like normal. If I write phosphate right next to it, notice I don't have parentheses around it, and that's because I only have one of it. If I only have one of it, then I don't need parentheses because it's just by itself. Lithium doesn't need parentheses because we already know that this 3 here is just going to this element. If I had multiple PO4s, multiple phosphates, I would have to put parentheses around it. But since I don't in this case, I only put it down after the lithium. Okay? I realize polyatomics still might seem confusing and or intimidating. I'll remind you when you're looking at things like names, just look for a name that doesn't sound normal. In your worksheet, though, you'll see that a lot of them are not in this type of format. They'll be like this, like these. And the way that you know it's a polyatomic ion is you look at what makes it up. You look at the chemical symbol and you can see that it's different. You can tell because the difference between something like NaCl is, notice that this has Na. Remember, this is a sodium because it has a capital letter and a small letter, the upper and lower case. If you have a uppercase letter, that means that you have a new, like, that follows it, similar to like if I had NO, for example, and this is a capital O, that means I have 2 elements here. This one is 2 elements. Okay. This one is 2 separate elements here. This is an element, and this is an element because these 2 letters are capitalized. For every capital letter, that's how many elements you have. This one has 2 elements, and this one has 2 elements. Even though this one has 4 letters, and this one has 2, this one has 2 capital letters, and this one has 2 capital letters. Your capital letters show you your elements. Okay? So, for example, like chromate down here, you'll see that it has C, R, and O. This R, though, is small, so that means, and the C is capital, so CR is one element and O is another. Okay? So if you get confused and go, this thing that I'm supposed to make has lots of different letters in it, most likely one of the things that you have on there is a polyatomic ion. Okie dokie. So make sure you have both your periodic table and your your polyatomic ion chart handy. If you have any questions, let me know. I think I've been rambling on long enough about polyatomics. If you'd like more help, let me know, and I can try and explain this idea easier for you. Okay? All right. Talk to you later, physical science. Bye.